This is section 3.3, and we're looking at a couple theorems on kind of the size needed for a subspace. I guess that's kind of what's happening here. So, how many vectors do we need? And they start with theorem 3.3.4, and it says every subspace of Fn, okay, Rn, can be, doesn't have to be, but can be represented in the form in the subspace S in this form, where they take x1 to xm, okay, those vectors, where m is less than or equal to n. So what this is saying is I can describe every subspace in, say Rn with no more than n vectors. Okay? So if I want to describe R2, I never need more than 2 vectors for any subspace of R2. Any subspace of R10, I never need any more than 10 vectors. That is what this is telling us. And so they give a proof. They say if S is just the 0 vector, there's nothing to do. Okay. In other words, they take x1 is the 0 vector, and there they've described it, and that's one vector. And so if we're in R1, R2, R3, R4, any of those, well, I just need the one vector, and so that's less than n, or less than or equal to n. And so there you go. That if it's just a 0 space. Okay, so, therefore, after that, we assume S has they say a non-zero, so has I would probably say at least one, but anyway, a non-zero vector x1. Okay. Now, if that's the case, then if we just go with that, that's a subspace of S as S itself is a subspace. Okay, so so we have that. Now, if that's all S is, they say, you know, if S is just this is equal to that subspace generated by X1, then, you know, we're done. We're finished. And if not, okay, S will contain a vector x2 that, and they say is not a linear combination of x1. Now I'm going to say that is not in x1. Those are the same thing. So I'm just pointing out that I could say it as x2 is not a linear combination of x1, but I can also say it's not in the subspace generated by x1. Okay? Either they're synonyms. Either way is fine. Okay. Now, if that's the case, then okay, then the subspace generated by x1 and x2 would have to be a subspace of S. Okay, because x1 and x2 are in S, so every linear combination of x1 and x2 are in S. And then they just keep going. Okay, so if what we just came up with is S, we're done. And you guessed it, right? If not, there is an x3 not in x1, x2, or in other words, it's not a linear combination of those two. But there's an x1 in S that's not in those. Okay, and so they say, well, this process must eventually stop. Okay. Now, there's the big question. Process must stop. Okay. So, and they say at stage K, we've constructed a family of linearly independent vectors x1 up to xk. All right, so these have all been linearly independent. This is based on our previous theorems, theorems 3.3.1 through 3.3.3, and these all in your F sub n. Okay, and hence k is less than or equal to n. And so they're saying it has to stop because at any given stage, right? We've constructed a linearly independent set, all in Fn, and that's the important part here. So I have a linearly independent set all in Fn, and if we go back to, I think it's 3.3.1, that was that original theorem that says if I have more than n vectors, right, if k was bigger than n, they couldn't be linearly independent. So that's the part where they're saying it must stop. This k could never get bigger than n and still keep this process going where we find something that's linearly independent. Okay, so it's using 3.3.1 in saying that, if I'm in Fn, a linearly independent set must have k generators, or k vectors, which is less than or equal to n. So that was 3.3.1. But the process that says, hey, we can keep this going until then, if we have to, was theorem 3.3.3, where we, just built up a linearly independent set, sort of one vector at a time. Okay, so we needed both of those theorems to get this theorem 3.3.4. Okay, but this is important in that it says if I let s equal 1, 1, negative 1, 1, and 0, 2, it says actually I can represent S with fewer vectors. Now, I don't know if I can represent it with just one. Well, actually I do, but I know I can't. But I do know I could represent it with either, maybe a 1 or a 2, but definitely no more than 2 vectors. I don't need any more than 2. Okay? I don't need any more than 2 vectors. Okay, and well, we'll call that video done. We'll do the last theorem in its own video.